Good afternoon, everyone. Those who are online and those who are here. So we're gonna start about now this webinar and seminar about a causal component-based modeling of process systems. Now we have today Dr. Christopher Rakaukas. So Christopher Rakaukas is research affiliate at MIT. He's also the PF Modeling Simulation at Julia Hub. Also director of scientific research.
And from the state, yep.
Thank you.
For now, that's it.
Also the big developer of the Scion Medical System in Julia. So we're glad to host him here today to talk about the hierarchical causal component-based modeling use modeling for JL, which is a library in Julia purpose. So I hope you enjoy. If you have any questions, I think you can just raise your hand, or if you're online, you can just send in the chat. Then whenever we do the pause to ask to answer the questions, we can make it.
All right.
So, please, Chris. Well,
all right, cool.
First.
So thank you. Yeah, I'm sorry that there's been a bit of a schedule change, but we'll. Is the recording started? That's the recording is started. All right. So yeah, so you'll be able to get the recording, and you'll be able to see the whole thing. If you do join an hour in, welcome already. Well, I guess you're not there all right now. But so as just a quick start, who here is familiar with acausal modeling? All right. Who here is familiar with Modeling Toolkit in some capacity? With differential equation solving? And with Julia? All right, so we got like a range of folks in the room. And if you raise your hand on your own computer online, I couldn't see it, but I'll make assumptions about it. So what I want to do first is I just want to introduce what Modeling Toolkit is all about. And then I want to kind of go through, after we kind of introduce what Modeling Toolkit is all about, I want to really go through the details of how do you build these acausal models, specifically in a way so that way you can build code that is reproducible. So let's say you build a model of a car, someone else builds a model of a battery, you can stick the model of the car and the battery together and you get the composed model of the whole system, and that allows you to be able to build these huge models in a way where everyone's building little components, right? That's what we mean by hierarchical component-based modeling. It is a modeling system so that way you can build complex, digital twins of objects independently, but then you're able to compose them together, and then you get the model of all the things composed together, right? If you think about, your own code and what happens with your own code, you always go, okay, I have this code that does a battery, and then you might have another PhD student that's in your same lab, like they've worked on a car. They don't stick together, right? It's not trivially just say cut and paste this code goes on top of this code. Now generate the composed set of equations. Oh, and you know what? This variable should be equal to this variable. Let's set up all the equalities. We get this differential algebraic equation system. That doesn't necessarily happen automatically. The Modeling Toolkit is a tool that will allow for this kind of work reusability to happen automatically, right? So first I want to talk about acausal modeling and industrial modeling and simulation, right? So I want to talk about first, how is Modeling Toolkit used? What are the things that we're doing with it? Just to kind of give you an idea of, what I could do with Modeling Toolkit, right? So again, so first of all, everything in Modeling Toolkit is based around the idea that you can do acausal modeling. And of course, we will go into exactly what that means in the near future. But what it's truly about is this, don't repeat yourself kind of idea. It's this idea of if someone built a detailed model of a battery, just plug that battery into your circuit, plug that battery into your electric vehicle, and you can reuse all these different models that people are building. And this also allows you to kind of give your model in a way that is reusable within graphical user interfaces. And so we're building lots of tooling on top of that as well, right? Modeling Toolkit is heavily inspired by Modelica. How many people in this room are familiar with Modelica? All right, so some people have kind of heard of it a little bit. Yeah, so, it is something that is, Modelica was started in Scandinavia, so you do find that, it's not the most popular thing in the world, though it is relatively known around the Scandinavian areas as a, modeling language. We'll describe a little bit what's different from Modelica here. But, there's a lot that's inspired Modeling Toolkit from Modelica. Modeling Toolkit, similarly to Modelica, comes with standard transformations. So if you know things like Terry and Pantelidis algorithm, these things for making different algebraic equations that are hard to solve, making them easy to solve, that's all in Modeling Toolkit. And We come with a open source standard library, and it's based on the Modelica standard library, right? So there's a lot that carries over. And we also have a whole team of programmers that are building out these larger digital twins for things like HVAC systems, battery systems, multi-body robotics, right? So this is, I have two different hats. I have this MIT hat, and I also have the Julia Sim hat, or at Julia Hub. And, so we're using the same underlying system, the same underlying open source components, but then we're building out these, industrial scale battery models and such for automotive and aerospace industries. You can see how Modeling Toolkit is used. There was a group. In fact, I highly recommend just watching Brad's video he gave at JuliaCon back in 2022, where he talks about this car catapult that he worked on. Right, so this car catapult system is, so you basically put a car on the sled, and what you do is you crash the wall crash the wall into the car instead of the car into the wall. Right, what I mean by that is you put a car, you put it on the sled, and then you push it backwards. And you can basically try to give it the same force as though the car was crashing into the wall to be able to measure what it would do to a crash dummy, right? And why would you do that? Well, this allows you to be able to check whether your car and its safety, safety elements, whether they will pass a safety test without actually crashing a car into the wall, right? And the reason why that's useful is because prototype cars can take millions and millions of dollars to build, and so therefore you can reuse your prototype over and over in this kind of test environment, right? So this was the situation which used to move to a very early version of Modeling Toolkit and Julia Sim. If I remember correctly, when they moved from Simulink, right? So Simulink is kind of in this world of tools that are covered by what Modeling Toolkit does. They moved to Modeling Toolkit, and they got an over 1,000-fold performance improvement, and then they were able to start working on this inverse problem. Why is there an inverse problem? Well, the inverse problem that's involved here is, what you want to do is you want to be able to say, okay, let's make the crash dummy move like they just got into a car crash on the highway, right? That would be like a force of, you're going like, I'm not going to know how to do it in kilometers per hour. So if you're going at 60 miles per hour, right? You're going 60 miles per hour on the highway, and you would have crashed into another car, right? So there's a certain force profile that and acceleration profile that you want to put on this crash dummy, right? But you don't actually directly control this, right? This is a control problem. You control how these hydraulics work, right? So there's these two giant pistons that you can control the hydraulics on, which are then controlling everything about how the sled works, right? So you build a model of this whole system. Then you ask the question, if I want the sled to go with this force, then how should I be doing my hydraulics, right? And so this kind of problem, and then being able to solve the inverse control problem, was able to be done in Modeling Toolkit in a way where you actually built one version of the model, and then there's a way to automatically solve the inverse control problem as part of effectively a transformation on the model. We're doing a lot with integrating neural networks and building digital twins with this, right? So, again, in this talk, I'm not going to go into any detail about scientific machine learning. I think I did that last time I was here. But basically, we can do things like we can take these components, model missing components or missing physics as neural networks, and then use that to be able to enhance the models that we build with the system, right? So someone can give you a model of a battery. You can say, well, I want battery with degradation. Here's data for degradation. You extend their model automatically, and then you use it for other pieces. So this is then what we're doing as Julia Sim, which has a lot of these open source pieces, but also has extra libraries in there, right? So I just want to kind of give a flavor for how this whole ecosystem around Modeling Toolkit is being developed. There's graphical user interfaces, VS Code plugins, and many, many other things being added. But okay, for some of you in the room, if you're already a Julia Modeling SciML user, right? Let's say you use differential equations and you're used to calling differential equations directly, or even if you just use MATLAB's ODE solver, or you use SciPy's ODE solver. If you're that kind of person, what can Modeling Toolkit offer you immediately, even before you get to ACLs of modeling, right? So one of the core things is that it handles a lot of very weird systems that can come up in types and modeling, right? So here what I'm showing is in a very natural kind of form. I'm saying I have, t as my dependent variable, and I have t as my independent variable, x as my dependent variable. And now I'm going to do a bunch of weird things to it. I'm going to say, the derivative of x with respect to time. Oh, that's normal. Here a times x of t, that's normal, right? But here, a times x of t minus tau, right? You might notice that this is a delay differential equation. Normally in, if you're to use some kind of solver library, you'd have to switch to a new library now to handle the delay differential equation. But here I'm also going to say, eta is a Brownian motion, right? And so I have this Brownian term here. So this is a stochastic differential equation. Actually, this is a stochastic delay differential equation, right? So I have delays in there and stochasticity in there. And so there is one set of solvers that's ever been built for solving stochastic delay differential equations. We built it in Julia, but you don't need to really worry about that. You just say, build this system, build a stochastic differential equation problem, and then solve it using one of these SDDE solvers, right? It turns out that most of that syntax is almost exactly the same between the ODE case, the SDE case, SDDE case. The only difference is you just have to declare, I have this type of problem here. And now actually, if you don't do that correctly, you'll get an error message that effectively tells you what direction to go with that, right? So what this means is that, there's all these different cases of models where you say, okay, I have a model, but now I have some randomness in my model. And the values that I'm using, well, maybe there's a delayed reaction here. Or, if I have a chemical reaction, maybe the chemical reaction is based on the amount of things that are bound and how many things are bound. The binding process takes a while. So I want to use the value of things that are bound 5 minutes ago. And all these modifications in the model, they're all kind of handled automatically with a lot of nice optimizations under the hood, because the symbolic system kind of understands all these levels of details in the potential for things for models, right? Now, I want to kind of highlight a sophisticated feature that really shows, why you might want to use a system that has symbolic pieces up front before the modeling simulation layer, right? So here, what you're looking at is a discrete simulation, right? So if you know your chemical reaction syntax, right? This is 2x plus y goes to 3x, right? So this is called Catalyst. It is a package built on top of Modeling Toolkit for representing chemical reaction networks using chemical reaction syntax. Where you say this is my rate and this is my reaction, and you build up a bunch of reactions, right? Now, you can, using Catalyst, you can say, now generate the ODEs that correspond to chemical reactions, and you solve it. You can say generate the stochastic differential equations that correspond to it, right? So you can generate all the different forms. Though here what it's showing is that you can actually run this in a discrete form as well, right? So you might know this as a Poisson process. You might know this as a Gillespie simulation. That depends on your background, what you might call it. But there's a lot of different names for this kind of process within the literature. But here we just say, for this chemical reaction, build the discrete form of it. This jump problem, and then solve it. We have a discrete one, right? Now, I could just have easily have said, build the OD problem of it, same code. Build the SD problem of it, same code. And you get the different representations of this chemical reaction, right? But okay, so what else can we do with this, though, right? Well, if you understand the model at a symbolic level, then you can also do approximations to the model on the fly, right? So what are some nice approximations? Well, okay, so here I'm showing that I could take the same model and I say ODE problem and I solve it, right? So this shows that some of the nice things with a symbolic modeling system is that you can have one representation of a model, and then you have different ways of solving or approximating such a model. And one system can kind of automate the process of moving between different levels of approximation, right? But okay, so what else can you do with such a model? Well, one of the things that you might find in the literature is that if you have a Poisson jump process where you say, okay, I have a Poisson probability of a reaction occurring according to the reaction rate, et cetera, what you can do is you can ask the question of, writing out all the moments, right? So if you know your mass action kinetics representation of chemical reaction system, mass action kinetics is the ODE that you get for just how the mean flow happens, right? So if you take this Poisson process and you only take the first moments, then you get an ODE that is called mass action kinetics, for how which is basically, without any noise, without any randomness, here's how the concentrations of the chemicals change over time if you have high enough concentrations, right? But it turns out that you can just say, instead of just the mean, you can also do the variance, the third moment, the fourth moment, all these moments beyond it. And then you can say, okay, from that same exact model, give me the generalization of mass action kinetics which gives me not just the mean, but also the variance of each component. And now solve the ODE that tells me the mean and the variance at each point in time, right? And so this shows that, this is something that is much more complicated in chemical reaction, right? You normally think, oh, chemical reaction, I either have to do this full discrete simulation, or I have this stochastic differential equation, or I have, mass action kinetics for the ODEs. But it turns out that there's many different levels to this, to the model they can have, and it can generate all sorts of approximations. And pretty much anything that you can consider doing to a model by hand as a math, by math, you can find a way to be able to write that same math as a symbolic manipulation, and now you have a tool that generates that version of the model for you for each new chemical reaction system, right? One of the other nice things that happens with Modeling Toolkit, which I won't get to today, though I know that some people here are working on this, is that Modeling Toolkit also has syntax that extends all the way to PDEs. So you can write PDEs in a very nice mathematical form. So here's, for example, a Poisson equation. And then you can tell it to discretize and solve the partial differential equation, right? It transforms partial differential equations into nonlinear systems, optimization systems, and ODEs, solves the underlying form, and then it gives you an interface to be able to interact with it back, right? And there's a lot more PDE interface stuff that's coming soon. So that's, some of the ways that you can use Modeling Toolkit. So now let me kind of get to the core, like what truly is Modeling Toolkit then, right? It's this thing that can do all sorts of weird modeling things and makes modeling easy, but what does it truly do, right? So let me kind of show this core a little bit now, right? So what it really is that Modeling Toolkit is a modeling system that is built on top of a symbolic system, and that symbolic engine has a lot of different symbolic tools for manipulating expressions, right? And so let me kind of break down this. So here, this is just a very basic Modeling Toolkit model, right? This Modeling Toolkit model is a second order ODE, right? It says, okay, so here I have, my first parameter is just the independent variable, right? But then I have a few parameters. I have a few dependent variables, x, y, and z. I have d, which is the derivative with respect to t, right? So that's just d dt. And now what I do is I just write my equations down, right? So here's the second derivative of x with respect to t is equal to, sigma times y minus x, yada, 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 right? So I just write a bunch of equations, right? And this is actually using symbolics.jl, right? The syntax is actually not Modeling Toolkit at all. It is symbolics.jl. It is the symbolic computer algebra system that we built within Julius. What I mean by that, well, how many have you used like Mathematica before, or have you used like SymPy? I think that there is one built in the MATLAB, right? So this is just like a symbolic modeling language, right? You can do things like ask for the symbolic derivative, ask for the symbolic integral, and like all these different expressions they can do on symbolic equations. This is just an array of symbolic equations, right? Now the next bit then brings in Modeling Toolkit, right? So a modeling layer on top of the symbolic layer, where we say, build this set of equations, these three equations is an ODE. So these three equations represent an ODE system, right? That imbues these equations with a bit more knowledge, right? They're not just three equations that live out in the world. They are now these three equations as a set defined an ordinary differential equation, right? And once you have that higher level of knowledge, you can do things to them, right? So for example, let's say you want to, the pass there that we're doing, right? So let's say you have a second order differential equation, x prime prime is equal to a parameter p, right? What you can define is you can say, I have a new variable v, which is equal to x prime, right? This is like the velocity, and that's position, right? And if you do that, you can rewrite your system instead as x prime is equal to v, and then v prime is equal to p, right? So this is called the first, so this is a first order ODE, and then this is the second order ODE, right? So this one has two derivatives, but if I define this new variable right here, I could get a set of equations in terms of one derivative, right? Hopefully that comes out well enough on the video. So what that means is, I can say, oh, if I have x double prime is equal to p, that is equivalent to the system that is x prime equals v, v prime equals p, right? And that's what this is doing here, right? It's just saying, hey, take this second order ODE system and do this simple transformation here. Transform it into a system of first order ODEs. And now, the ODE solver requires a system of first order ODEs. So let me solve it using that, right? So you can say, oh, my initial conditions are an initial condition for x, initial condition for y, initial condition for z. But notice that we actually will have an extra equation in there, which is due to the derivative. So we also have to give the initial condition for d of x, right? But this symbolic system then has taken care of that transformation to this new form, and then you can solve build the numerical solver problem, and then you solve it, right? This last bit right here is the differential equation solver, differential equations.jl, right? So you can see that Modeling Toolkit is really this layer in the middle that is, give me symbolic representation of equations, and I will do things with them. I will change them around, and I will build a better form for the solver to then be able to interact with. And so you can almost think about it as then it's a modeling front end to a symbolic ecosystem. There's a lot of symbolic tools that we have underneath the hood that we're just exposing in a way to modelers. And so what are some kind of why would you want to have a symbolic system involved in your modeling tool at all, right? So let's look at something that's not an ODE system, but a nonlinear system, right? Well, a nonlinear system arises if you just have a bunch of equations and no derivatives, right? So, and they will show up in algebraic equation systems or differential algebraic equation systems. They show up all over the place. So here's a set of 5 algebraic equations, right? Now, you might, this is how you might be given the problem, or you might come up with a model this way. Now think about it as you instead write down, one case where it will come up often is if you're solving for steady state, right? If you're solving for the steady state of 100,000, chemical species, you just write them all down, right? Now, the key here is that, there might be implicit relations inside of it, right? I mean, the way that I've written these equations should be very obvious that this is effectively U1 equals sine of U5, U2 is equal to cosine of U1, yada, 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 right? But effectively, there's something else that's involved here, right? It turns out that you only actually need to do Newton's method on one variable. What do I mean by that? Well, if you call structural simplify on this nonlinear system, what you get is it just says the equations for the system is just 0 equals U5 minus U4 U1, right? Well, what does that mean? Well, if you actually look at the observed variables of the system, you'll find that it says U1 equals this, U2 equals this, U3 equals this, U4 equals this, right? So what structural simplify does to your quick set of equations is it looks at your set of equations and just says, is there a subset of the equations that you actually have to solve for? And can I write the other variables as explicit functions of the subset that is solvable? Right. That's one of the things that the structural simplification does. And this will go into a lot of other details on other algorithms that it's applying. But that's effectively what it does here, right? And if you look at it, you see, okay, U1 is sine of U5. U2 is cosine of sine of U5. U3 is hypotenuse of sine of U5, cosine of sine of U5, right? You see that everything here is just reduced down to U1 is a function of U5, U2 is a function of U5, U3 is a function of U5, U4 is a function of U5. So we actually just have a scalar nonlinear solve. And so you don't need to use a 5 by 5 Newton method. You can use a 1 by 1. You can just use a scalar Newton method in this case, right? And so, so again, this is the same thing. It's just a symbolic transformation of your equations. It's taking the equations that you give it, and it's finding a simpler set of equations to solve. And that's what this structural simplification, or one part of the structural simplification, does. Now, because your numerical solver is no longer acting on the same state space that your original equation was, it also bumps the symbolic level all the way up to the solver, right? So what I mean by that, so if you solve this set of equations, again, so this is actually the same runnable code from before. So you build this set of equations where you say, I have 5 variables, right? And then you call the nonlinear solver, right? It's the same nonlinear solver like fmin or in MATLAB or like scipy.solve, right? You call the solver and it gives you out a vector of one thing, which is weird. You're like, I gave you 5 variables. Why'd you only solve for 1? Well, it implicitly knows how to build the other 4 on demand if you ask for it. So then what you do is you can index the system where you just say, give me the solution of U1. Again, that's a symbolic variable, and it understands the solution of U1 is this thing. Solution of U2 is this thing. Now, if it actually solved for it, right, if you ask for solve U5, it'll give you the value that it's actually solved for. If you give it solve U1, then what it'll do is it'll do sine of the thing that you solved for. So this is sine of 1.6, right, which is pretty close to pi, which so you can kind of eyeball, right, or pi over 2, right? So you can kind of see that, okay, the system is automatically simplifying down what I'm numerically solving and solving the smallest version of the problem that is required. And then if you ask for observables for any of these observables, it has a way to reconstruct them, right? And so you can already kind of imagine in your head where it's like, okay, I might be writing down models in a way that is not necessarily, I haven't completely hand optimized every little detail of it. Well, Modeling Toolkit can then go through and simplify out a lot of the variables and before solving. And then this can improve not only the this not only improves this performance of doing numerical solves, but it also improves the robustness, right? Because if you have these equations that are trivial, like the concentration of x equals the concentration of y, you really should delete one of your variables and just plug them in there, because the different, having a small difference between the two could cause instabilities and all sorts of things during the solver process. And this makes it so that way it's fundamentally impossible, because it will have changed your equations such that they structurally have to be equal. And so there's a lot of different tools that are plugging into this whole system and using it as this kind of core transformation tool under the hood. I mean, if we're talking to a given group, each group has their own kind of set of tooling. But here what I'm talking about is Catalyst.jl is for people who do chemical reaction networks, a lot of times in systems biology. NeuralBlocks is a group that does computational neuroscience, and those models are also ODEs represented in here. Base Modelica is representation from Modelica transformed into here. There's pharmacometric models. Effectively, you have lots of different modeling groups that are targeting the same core, right? So that way, as you work in these different modeling domains, you can build up an interface where you say, hey, this is how I want people to build models, but I don't need to actually worry that I build a model in a numerically performant or good way. I offload that information to Modeling Toolkit, which will then instead transform the model to a good model under the hood for me and do that solving process. So what does Modeling Toolkit then do for the performance of difficult models, right? So I do want to kind of mention that there are some extra tools in this Modeling Toolkit ecosystem that are being built, right? So for example, we have an alternative compiler, which is this JuliaSim compiler that works on an intermediate representation form called an IR form. And it has some special compiler passes that are specifically for code gen, for if you have hundreds of thousands or more equations. And so, for example, if you have certain properties, like if you have a model with a lot of repeated components, like let's say you have a resistor, a RC circuit, but you have N resistors and N capacitors, right? If you think about it, in a modeling system, we're going to have to analyze the whole system, and it's actually a pretty hard problem for how to do the code generation. But if you were to think about this and actually derive it by hand, the code that you probably write would end up being like a for loop for every resistor capacitor. And so what the JuliaSim compiler is able to do is it's able to find the implicit structures and rebuild the loops there. In fact, it'll cut things out of loops and things like that based off of whether they're boundary conditions or whatnot. And so if you have really, really, really large models, then we have alternative forms of this compilation that is for handling these really big cases. I kind of want to skip over a little details here, just to kind of get directly to the mode. But there's other things that it does, like for example, if you build these models like in robotics, like multi-body systems, what you'll find is that you have equations like this, where you have some equations built in that are linear systems, and so it will do things like embed linear solves into it'll solve it. It'll get an analytical solution to some of the linear systems, and then it'll embed the linear solve into the equations that it's building, instead of having to do the solution of that linear system every single time. So there's a lot of little tricks that these things are doing. I just kind of want to kind of tell you, like, okay, that is so that's why you would use Modeling Toolkit. So even if you aren't going to do any causal modeling, in a lot of cases, using Modeling Toolkit is still a good idea, because it can take the equations that you give it and generate a faster way to be able to solve it, and then generate code for that using the tools under the hood, right? But that's one part of the whole story. Now let's actually get to the main theme, the entree of this, which is acausal versus causal modeling. So at a high level, again, I'm going to go back through this. I just want to kind of give you the pitch for why you should care about acausal modeling first. So acausal modeling is something that is used in a lot of software packages, right? I think that more software packages use causal modeling than acausal modeling. Probably the biggest one, which is taught in almost every mechanical engineering group, or a lot of engineering groups, is probably Simulink. So I'm sure a lot of people here have learned some version of causal modeling with Simulink. And so, the pro to causal modeling is that tons of engineers know it. There's, also, I think one pro that I forgot to put in here is that, it's much easier to build a causal modeling system, because causal modeling systems do not require the transformations. And I'll describe exactly why you need fundamentally a more difficult compiler for causal modeling, right? But the con with causal modeling is that you can do little changes to the model scenario that you're doing, and suddenly your model that you have is actually is not reusable at all. And because of that, there's a lot of tricks that you have to do to make it work in practice that that kind of make it less numerically stable and generate slower code. One nice example of this is handling of algebraic loops, right? If you've ever built these causal models in Simulink, and then they say, oh, I have to figure out how to tear these algebraic loops, and you find out that, hey, once I've added an algebraic loop to my system, it goes like 10 to 100 times slower, right? Well, it's because fundamentally, the way that you deal with algebraic loops shouldn't actually be through an explicit system. It's implicit, right? These, Newton's method and these kinds of things are really how you need to think about algebraic loops. If you say that things are equal, you don't handle equality just by functional iteration, right? That is one way to solve for inequality, but is not necessarily the most stable or convergent method that there is, right? So what is acausal modeling in contrast to that? Well, it is a modeling system that allows you to use a higher level description of the model, so that we can more easily reuse the equations in other systems, right? It tends to give you better numerical stability and compute performance, and it's more reusable, more hierarchical. There are two major cons, though. It's more restrictive on the available software because a lot more is done in the compilation stage, and we'll show this in practice, right? That's not just a statement of, oh, this is hard to do. I'll show you exactly what's going on under the hood, and then you'll be able to very easily appreciate why more people do not want to build acausal modeling compilers. But if one's already built, you might as well use it. The other issue, though, is that it's not as often. This is a very American-centric side. It's not as hot as often in American universities. In fact, you almost never see acausal modeling on the American side of the pond. So the fact that you've heard of Modelica here is kind of a sign that I'm in Norway, right? So, but even then, acausal modeling is still not as popular. Like everyone knows, seemingly coming out of an engineering degree, a small group that are in Northern Europe know about acausal modeling, and that's about it, right? And that's a con, right? Not as many people are using it, but also I'll tell you why, it's something that you should be putting into your engineering bucket, right? So to show you why you want to use acausal modeling instead of causal modeling, I feel like a show don't tell approach will work. So here's some elementary circuits, and let's do these completely by hand. Let's do these completely by hand using a acausal and a causal approach, right? So let's do this. Now, do we have a better marker here? All right. While I steal from the other room, I could talk this slide out. So I think that when I get to the next slide, I'll probably want to write a little bit more out. So the key here is, okay, so I have this RC circuit, right? The question is, what are my equations, right? So, well, first of all, what are your equations? The first equation is Kirchhoff's voltage law and Kirchhoff's current law, right? What are these? Well, if you remember back to your physics of circuits, I believe everyone had one class on physics of circuits all the way back maybe 10 years ago or something. So you'll have a reminder, right? Kirchhoff's voltage law is that the voltages in a circle all have to add up to zero. Or if you go around in a circle, then the voltages add to zero. Now, why is that? Why is that the case? Well, this is a statement of conservation of charge, or no, this is a statement of conservation of energy, which is basically that the energy is moving out of the voltage source has to go into the resistor and then has to go into the capacitor, right? So you basically have a conservation law that just basically then tells you that the voltage of the resistor plus the voltage of the capacitor is equal to V. Then you also have Kirchhoff's current law, which is a statement of conservation of charge, right? So every electron that is moving out of the voltage source is an electron that's going into the resistor, which is then an electron flowing here, right? If your electron flows around in a circle, then it has to be, the current of that electron has to be accounted for, right? Your electrons can't get lost is another way of saying it, right? So that's a way of understanding Kirchhoff's voltage law and Kirchhoff's current law, which will restate Kirchhoff's laws in a little bit. In a way that I think ends up being more understandable, but this is the general way that they're understood, right? So these are two Kirchhoff's laws, right? And why do I have this little subscript here? Well, because if you think about it, in the circuit, there isn't truly a thing such as the current of the circuit, nor is there the current of the resistor, right? So I have a voltage source and then I have a resistor, and then I have a capacitor, right? And there is a voltage of the resistor itself, right? What is the voltage? What is the voltage of a resistor? Well, if you think back again, doing your electrical circuit modeling, what you would do is you put your voltage probe, right? You put like one pin of your voltage probe here, one pin of the voltage probe here, and you'd measure the voltage that goes across the resistor, right? So the voltage of a resistor is the voltage drop across the resistor. Same thing on the capacitor, right? The voltage of a capacitor is the voltage drop across the two sides of the capacitor, right? So, so you don't really just have a voltage, you have a voltage of the voltage source, you have a voltage of the resistor, which is how much voltage is dropped through the resistor, and you have the voltage of the capacitor, you have the current of the resistor, which is the current flowing through the resistor, and the current flowing through the capacitor, right? So now if you understand that, then you go, okay, so I have multiple different things here, right? So I have the voltage of the resistor plus the voltage of the capacitor has to be equal to the voltage of the voltage source, right? That's then what Kirchhoff's voltage law is saying. And Kirchhoff's current law is saying that the voltage flowing through the resistor, I sub R, is equal to the current flowing through the capacitor, I sub C, right? And so you have those laws, and so everything, that's what these subscripts mean, is the voltage of the resistor and the voltage of the capacitor, right? Now you have your device equations. V sub R, so the voltage of the resistor, equals the current of the resistor times the resistance. That's just Ohm's law, right? V equals I times R, your classic Ohm's law. Your other equation is I sub C, so the current through the capacitor is equal to the capacitance times voltage of the capacitor dot, right? This is the capacitance equation, right? The derivative of the voltage in the capacitor is equal to the current over C, right? So these are just, you can look these up on Wikipedia, right? These are the four equations that describe the RC circuit. So now that we've described the RC circuit, how do we actually get a model, a runnable model from the RC circuit, right? Because I gave you four equations. I didn't give you a simulation at all, right? What you would do is you'd say, okay, well, let me manipulate my equations a little bit, yada, yada, yada. After, you take, let's see, you take this equation right here, you substitute VR is equal to V minus VC, yada, yada, yada. Right? So if you stare at the equations long enough, you can do the whole thing out. And what you get is that V sub C, so the voltage of the capacitor dot, its derivative is equal to V minus VC over R times C, right? So now we have an equation that we can use. Let's build a model for the set of equations that will then be able to represent the system, right? So how would we do this inside of a causal modeling system? Well, remember, in a causal modeling system, we have things like gains, integrators, we have gains and integrators and adders. So you can come up with, so here's what you do if you build like the Simulink-ish type of circuit on this, right? What you do is you take whatever represents V, you would use your adder to the gain of 1 over, the adder to VC, and then you'd put the gain on it, 1 over C. Now, this is kind of incomprehensible for me to say it, so let me just show you the picture. Here's the Simulink causal circuit, right? This is what you probably would have had to do in one of your, exams in your first year of engineering, right? So you'd say, okay, so I have this value V, or this is my constant, and I add it to something else. Let's figure out what we're adding it to in a second, right? So we take whatever's added together, and we then multiply it, right? So this is a gain, 1 over RC. Then we run it through the integrator, so and then we multiply it by -1, right? So what is the arrow coming out from here? Well, that must be VC, right? Because this is V plus, or V minus VC, right? Because that's why this minus is here. And so, V minus VC divided by RC, we integrate it, right? Because the dot right here, you change the dot expression to VC itself by using the integrator. And so this path right here is computing VC, which goes back into here. And so this is our causal model, right? Now, that's not probably the, okay, so we just did the RC circuit from scratch, which would be like one of your undergrad, day-long classes or something. But okay, it's not so bad to do it like this, but, why did we have to do all this math and everything, right? So one of the issues that you can run into here is that, here I'm saying I have a voltage source, right? If I instead said I had a current source, then I have to do a completely different thing here. You'll find that your equations are actually completely different in the end, right? And then what that means that if I had a current coming in, actually now I'd actually have a whole completely different model here as well, right? It just turns out that small changes to the model end up giving you small changes to the model's representation, or large change to the model's representation. But what's the A-causal model? Well, the A-causal model is exactly this. It's just, we just say I have a resistor, I have a capacitor, I have a voltage source, and I connect them. Right? You just say, okay, take the positive pin of the voltage source, and it's positive pin of the voltage source is now the positive pin of the resistor. We connect the negative pin of the resistor to the positive pin of the capacitor. We connect this back over to the source. We also have a ground here. So the diagram is not showing ground, but there is a ground that you need to ground your system, right, in order to know what zero means. But okay, that's my whole system. Boom, it's the same mathematics, right? Now, okay, the question that you should have is, okay, what the heck is it doing under the hood? How do I know that it's the same equations? Why is it able to be easier? And we'll build into this. We're going slowly, right? But to really see the advantage of a modeling system that is one level higher like that, you start have to say, okay, what do we do if we have the RLC circuit, right? Now the RLC circuit looks very similar to the RC circuit, but because we have put one more thing in our loop here, we've actually changed our voltage law, we've changed our current law, and we've actually then added one more equation. But because we've changed our voltage law, it turns out that this is a fundamental change in the way we do the calculation. And so if you actually then solve for your equations, you find out that you don't even have the VC minus V term in here. It doesn't even show up in your equations at all. And so the way that you represent this RLC circuit in a causal model is almost completely different from the way that you represent the RC circuit in a causal model, right? So here it is as a causal model. Again, if you really want to work it out, you can work it out. It's just gains, adders, and it's just gains, adders, and integrators, right? So it's your very basic, Simulink 101. But still, even with this kind of model, the point is that the point is that well, if you actually look at the difference between the RC circuit and the RLC circuit, I've highlighted exactly which equations are different in there. And what you find is that you barely have any shared components between the two, right? Once building the causal model for the RC circuit gives you a model, building the causal model for the RLC circuit is almost a completely different model because the way that you actually do the calculation is completely different, right? But if you then look at the A-causal model, it's almost, all that we do is we just added that, hey, look, there's an inductor in here, and I do a few more connections. So the A-causal model is almost exactly the same as what it was with the RC circuit, right? You just stick an inductor in there and you just say connect things, right? So this shows why it's very reusable, right? If you already had models for resistors and capacitors, and just tell me how to connect them, and I'll just connect a new thing in here. Okay, we'll fix it up, and now boom, you now have a model that's runnable, does the same thing, but you don't have to do all this rejiggering for every little detail that changes in the model. So you should be looking at this and go, okay, you must be cheating somewhere, right? Like there's got to be some hard work, under the hood somewhere for how you do this, right? Because if the calculation is truly different, who's figuring that out, right? And so now I want to show you how the A-causal model works, kind of get a deeper understanding for why it's able to achieve the simple form. And so the way that the A-causal models work is through their connections, right? So let me kind of describe this part in a few different ways. And I'll say that you should probably you should feel like you understand A-causal modeling at about 20% right now, right? So if you feel like you're still not getting exactly what it is, that you're still in the right spot, right? So now let's get that up to about 50%, right? So what is A-causal modeling actually doing? Well, A-causal modeling is all about the definition of its connector semantics. So what do I mean by that? Well, let's think about what happens when you connect circuit components, right? So we have a connection here between different circuit components. We have the voltage source and the resistor that are connected to the same spot, right? Now, what should happen when you connect two wires together, right? Well, what will happen almost instantaneously is that the voltages will align, right? If you have a voltage drop, you have voltage drop over components, but if you have a short circuit, a wire, right, then what happens is that you have a connection instantly, and you're going to get that voltage drop to effectively be zero, right? So if you connect two wires, then what happens is that you have at this point right here, you have to have the voltage of this voltage here and the voltage coming out here have got to be the same, right? But now, if you then think about current, right? Well, current is such a thing where, if you're tracking a little electron guy, right, and it's going around, right, whatever electron comes out of here has to go into here. And so the current coming out of here plus the current going into here must always be equal to 0. Right, that's just another statement that your electron has to, if it's coming from somewhere and it goes somewhere, you have to have the equal come out that goes in, right? So what this means is that you kind of have two different types of variables. You have some variables where when you connect things, they have equality, and you have some variables that when you connect things, you sum them to 0, right? So what are some other examples of this? Well, another example of this is actually if you think about, translational components, right? So let's say think about, you have, if you have a gear, right? A gear is moving around in a circle, right? The gear will apply a force to another object, right? And where the two are meeting, right? What does Newton's law tell you? Newton's law tells you that the force that is coming from one of the objects has to be equal to the force going on the other object, right? And their velocities then have to be opposite, right? If you have one that is rotating this way and one gear that's rotating this way and pushing it down, well, then the other one has to be moving in the counterclockwise fashion, right? And so you end up having this relationship between force and velocity. Think about it now in terms of fluid flow or mass flow, right? So you have that, if you have a pipe, right? So now if you have a pipe and you connect this pipe to another pipe, right? Well, the mass that is going through this, you have to have that, whatever mass comes out of here is mass that goes into here. So that's a flow variable. But then what is the thing that is equal? Well, the thing that is equal is the mass, is the, the concentration flow, that velocity variable, right? Because whatever is that, whatever is flowing out has to be equal to what's flowing in, right? And so you end up having this kind of natural relationship between variables. Turns out that this is actually something that's more fundamental in physics. Why is it always these kind of, some things are equal, some things are adding? Well, if you think about these as Hamiltonian systems, right? If you have a Hamiltonian system, so h of p cubed, right? And you've done your Hamiltonian dynamics, you have one set of equations for dh dp, you have one set of equations for dh dq, and it turns out that that the difference between your what variables are connecting by adding or versus the variables that connect by equality is just the difference between the p and the q's in your Hamiltonian. So it's actually, this is a very fundamental fact of physics that might not have been expressed as much, right? So now let me bring this one level higher, and we'll kind of describe what this RC circuit is component by component to be able to kind of show you how you would build a electrical circuit model, right? But then if you go to each domain, whether you have translational, magnetic, or chemical reactions or whatever else type of system, you'll be able to see how you would use this connector semantics to basically build these reusable components. So okay, let's talk about this every single thing that is involved in this RC circuit model, right? So the first thing that we're going to do is we're going to define a pin, right? A pin is a point of the electrical circuit, right? And so how do we define a pin? Well, any point on the electrical circuit, any point on this electrical circuit, like a little dot right here, has a state that has two things, right? It has a voltage and a current. And voltages, again, are the things that connect by equality. So I'll say that it's just a standard connection. And current is something that connects by flow, right? So this is the type of variable that connects by adding to 0 at a point. And so that's all that a pin is. A pin is a thing that has a voltage and a current. Again, you should only be at half of an understanding right now. You're just like, okay, what does this even mean? I just have a thing that it has variables that don't even have any equations in it yet. So how does it do anything, right? So let's start building this up, right? So, okay, so now let's talk about a one port. A one port, so I hate the language here, but I'm going with the standard language from electrical engineering. And the standard language from electrical engineering is that a one port is an object with 2 pins. So what do I mean by that? So what is an object with 2 pins? Well, think about this resistor, right? A resistor is something that has 2 pins, a positive pin and a negative pin, right? A capacitor is something that has 2 pins, a positive pin and a negative pin. Voltage source is something that has a positive pin and a negative pin, right? So all of these objects are one port type of objects, right? So what is a one port object? a one-port object is an object that has a positive pin, we call it P, and a negative pin, we call N, right? Now, a one-port object, so all of these objects, right, have a state associated with them, right? They have a voltage and they have a current. So what are these equations here meaning? Well, this is saying that the voltage of the object itself is the voltage drop from the positive pin to the negative pin.
Can you just stop sharing your screen for a second? Is that possible?
Did I? Oh, rejoin? All right, sorry about that.
No, but it's from, the audio is coming from my.
Yeah. Okay, sorry about that. So the voltage of any object that has two pins is defined by the voltage of the positive pin minus the voltage of the negative pin, right? That is the voltage drop across the resistor. That is the voltage drop across the capacitor. That's the voltage drop across the voltage source, right? Oh, let me make sure I draw this grounding here, just to be more sane. So okay, so that's all that this is saying, right? The voltage of a two-pin object with two pins is defined as the voltage, the difference in the voltage from the positive pin to the negative pin, right? Now, what does this equation right here mean? Does anyone know? Can anyone guess? 0 equals P dot I plus P dot N, or N dot I.
Current flow.
Yeah. It's just the conservation of the current flow, right? Whatever current is flowing into the resistor has to come out of the resistor, right? So that's all that this is saying. That the current coming into the resistor equals the negative of the current coming out of the resistor, right? You just flip your negative over, and it's the two i's up. If you add them together, they sum to 0, right? Now, how do we define the current of the resistor? Well, we have to choose a convention, right? You could either choose it to be the current going in one way, or you could choose it to be the current going in the other way. So we define the current of a two-pin object to be the current going into the positive pin, right? The other plausible definition is it could be the negative of that, right? But okay, so this is a one-port object, right? So I didn't say that a thing that has two pins has these things being true, right? These are all just true. These are just all equations that we know to be true. We've already established them. Okay, so now what is a resistor? Well, a resistor is a one-port object, right? It's a thing that has two pins, but it also has a parameter R, that is the resistance, and it has one more equation, right? That equation is V equals I times R, right? So what I mean by this V, well, this V is the voltage of the resistor, which is the voltage drop across the two pins, right? So that V is equal to I, which is the current flowing into the resistor, which is equal to the current of the positive pin, right, times R. And now you can see that I actually have, this is not the only equation that defines a resistor, right? Because all these other equations also define how all these things are related within a resistor, right? But again, this is just the truth, right? This is just Ohm's law, right? I've just written down Ohm's law. This is just your very standard high schooler, physics, right? And again, a capacitor is just, the derivative of voltage is equal to I divided by C, right? So a capacitor is an object for which this equation is true, and it's also a one-port, right?
Oh, the screen sharing disappeared again.
Oh, yeah, Microsoft Teams is not the greatest thing. I'll try this again. Maybe it's edgy room and I'm at like some rate limit. But, Yeah, because it's saying that it's an internet issue. But I'll keep going, or I'll just keep on joining back in, right? Okay, so then what are the next things? Well, ground ground is just a pin, right? So ground right here is just a pin. Or what do we do with this pin? Well, we're just saying that its voltage is equal to 0, right? That's by definition what you would do in your physics class, right? It's just a point in your circuit where the voltage is defined to be 0, right? Now, what is a constant voltage? What's a constant voltage source? It is also a 2-pin object, right? It's an object with 2 pins where the voltage of the source, or the voltage of the voltage source, is equal to some constant, right? Now, you should feel like, you understand A causal modeling like 40% or 50% now. You're like, okay, every single equation that you've written down makes sense, right? Any equation that I've written down doesn't make sense to anyone? All right, so all these things are true. Ta-da, the model works. There you go. Okay, well, okay, I feel like I might have missed something, right? Well, let's actually just write it out then, right? So what's going on is if you ask the modeling toolkit or this A causal modeling system, hey, it's, give me the equations, but expand the connection, right? What you'll see is you just get a whole list of things that are true, right? So here, for example, the top one is that the resistor dot V is equal to minus the resistor dot N plus the resistor dot V, right? That is just saying that the voltage of the resistor is defined as the voltage drop between the negative pin and the positive pin of the resistor, right? Oh, that one's true. Let's look at the next one. This is the current flowing through the resistor, right? The current, the negative current in the negative pin of the resistor is equal to the minus of the current positive pin of the resistor. True, right? So all these things, all the equations that we had in here just show up in the list. But what else shows up in here? Well, we have these connection equations, right? Which is that at this point right here, we have that the positive pin of the voltage source is equal to the voltage on the positive pin of the resistor, right? Since we have a connection between the two positive pins, then since we have a connection between the two positive pins, that just means that those two voltages are equal to, right? And then over here, we also have that the current flowing out of the current flowing out of the capacitor, right? Or the current flowing into the capacitor is equal to the negative of the current flowing into the resistor. Yeah, I think I might have flipped the description, but it's just, this is another connection equation, right? So if you think about it, all of our equations are either equations that we've written down, just one of these simple truths, or they're a statement that comes from these connections, right? Where anything that you connected, their voltages are equal, but their currents have this, the currents sum to 0. So this is just a set of equations that is all of the things that we described as equal, right? Everything here is just either coming from a connection equation, either because voltages connect as equal, or currents connect as summing to 0, or they are a statement from from either the 1-pin definition or a statement from one of our components, right? And now the true trick of A causal modeling is that in this set of equations, we can call structural simplify. Again, remember, we have this thing, it's all a symbolic modeling language. When we just say, hey, structurally simplify this, and what it gives you is this one equation right here. Right? It basically says this set of 20 equations that describes the RC circuit is equivalent. You can equivalently just solve this one ODE, and you're good. Right. And then once you have that one OD, once you have that, then you have other equations that tell you how do you, and if dropping again. I mean, it said, sorry, we can't get you back in the meeting. Make sure you have an internet connection and rejoin. So
maybe there's a cable here, let's see. Maybe there's an internet cable.
Well, I can't do that with my laptop anyways. Well, we can figure out something in a second here, but I'll just keep going. Okay. So basically what happens then is that A causal modeling works by building a differential algebraic equation system that is stating all of the equalities within the system, right? And then it performs a structural simplification to give you the equivalent piece to solve, right? And then here RC circuit, of course, as we kind of derived by hand, turns into just one ODE, right? And so what it does is it basically just says, okay, here are the 20 equations that describe the RC circuit, but you can just solve this one ODE. But now if you want to know anything else, right? If you solve this one ODE in the ODE solver, it tells you what the voltage of the capacitor is. And if you're given the voltage of the capacitor, well, then the voltage of the resistor, all the other terms in the equation can all be reconstructed using these other equations behind the scenes, right? So you can then kind of see how what I mentioned before about structural simplification is then used in an A-causal modeling system to give you the full version of the model, right? So you write down something that has 20 equations, you solve one equation, but you get all the others, right? This really shows you then how an A-causal modeling system works, though, right? It's naturally a differential algebraic equation system because you naturally have differential equations that are encoded in some systems, and you have lots of algebraic equations coming from the equalities of connections, and and also the also you have the summation equalities, from the currents summing to zero, right? You have a lot of different equalities that you're writing down, and you basically just say, handle this system that has both different derivatives and also has these algebraic conditions on it, right? Now, in this case, it simplifies down to just having a single ODE, though in many cases you will still have equality system in there, right? So this is why you'll have some derivatives, and you'll have some constraint equations that are carried along with it. And so then the solver just has to handle both of those together as a differential algebraic equation system, and then it can do all this, right? So modeling toolkit's A-causal modeling system then is, it's in comparison to causal modeling system, it is simpler to extend, right? You can see very quickly what would you do if you had a if you had a thermal varying resistor. Well, you just change this equation right here, where your resistance is now some function of temperature. And how would you handle temperature? Well, temperature is also something where the temperature between, if you have a pipe, the temperature at the pipe is going to be equal, but then you have the temperature flow, which has to sum to zero, right? You always have these kind of relations. You keep going and going and going, but these components that you have can then be, you can, if someone else defines a transistor, you can use their million equation transistor model and connect your resistor to it, and it will be able to know how to easily build the system that is composed from that, right? And so it's naturally a system that is able to be extended faster to model large systems, but it's also numerically stable because if you think about it, we're dealing with a lot of algebraic loops in the way that we describe the system, but the way that we're dealing with these algebraic loops is we're treating it as a differential algebraic equation. We're not trying to find an ODE for the system. We actually treat it as something that actually has true constraint equations, and the solver then has to do steps to be able to enforce these steps along the way. And I'll probably not go into detail about that, but if you have any questions about how DA solvers work, I'd be happy to go into detail. But the code that you get in the end is clearly easier to read and easier to debug. I mean, I think that most people would think that this is what you would describe as an RLC circuit, right? This representation of the system looks like I have a resistor, capacitor, inductor, and I've connected them in this form, whereas I think it's pretty clear to most people that this does not look like an RLC circuit, right? And so there you go. Like that's how A-causal modeling works. Now I want to kind of walk through this step by step in practice, right? So for this version, so if you watch the version that I did for Julia Kahn, you will actually see that I had a whole step in the beginning there, which was going through symbolic numeric model definitions. So I go through using the computer algebra system first in order to do all sorts of transformations on your own. For this talk, I'm actually going to skip that so that way I can go to some of the other components that I didn't get to in the Julia Kahn version. So I'll go straight into the introduction to A-causal modeling via the RC circuit, right? So I'm going to go back through this RC circuit. And again, you should probably have, I would say, like a 70% understanding of A-causal modeling now. You feel like you're starting to get it, but once you see the code step by step, it should make even more sense, right? So what are we going to do? We pull in modeling toolkit, and we pull in, and we just say T is, we want to use the version of time that has no units, and we want to use the version of the derivative that has no units, right? And so the first thing is, let's just use the standard library to build the RC circuit, right? So the standard library has pre-built components. And so we can just use the components that come out of the standard library and connect them up together, right? So here I'm saying, hey, let's use the modeling toolkit standard library to electrical. Let's use the electrical components. Let's also use the constant component. Why do I want a constant? Well, because I'm going to want to have a constant voltage source. Let's define a few constants. R is equal to 1, C is equal to 1, V is equal to 1. I'm just defining some constants equal to 1. And now I build my model, right? So now let's go step by step through this code, right? So what I'm saying is, what are the components of this model? I have a resistor, and it has a resistance equal to 1. I have a capacitor. It has a capacitance equal to 1. I have a constant voltage with V equals to 1. I have a ground, which is equal to 1. Now, this one is actually a little bit different. I guess the code that I have here is from a slightly older version. So let me actually show you the slight difference here. Actually, so I mean, so in the newer versions, we don't have a constant voltage. We have a constant and we have a voltage, and you stick the two together. But I mean, that's just so that way we can reuse the same constant object across many different units and types and such. So for now, ignore that difference in the detail. This is also a bit one that's a bit easier. So, but okay, so I have this constant voltage source and I have a constant ground. And what I do here is then I just say, okay, I add my equations. So what are my equations for the RC circuit? Well, each of these components has equations that are already inside of them, but I can then add equations on top for this system, right? So what are the equations that I want to add to it? I want to just tell you how it's connected, right? The source of the voltage source is connected to the resistor. The resistor, the negative pin of the resistor is connected to the positive pin of the capacitor. The negative pin of the capacitor is to the source, and also there's a ground that is in right there, right? So my equations of my composed system are just what are the equations for generating for the connections, right? If you think about it, each of these is two equations, right? It's saying that the voltage of the source dot P and the voltage of the resistor dot P are equal, and this is also the other equation that says the current of the source dot so source dot P dot I plus source resistor dot P dot I is equal to 0, right? The currents have to be equal to 0. So that's why it goes under equations. Connecting two pieces or connecting two components together is the same thing as describing two equations, right? Or n equations, depending on how you have these connections set up. So okay, so then what I do is I just say, okay, MTK build. Let's build this model. Let me show you how this looks inside of the REPL, right? So let me make this REPL a little bit bigger. So I run this, and then I say MTK build, and actually runs the simplification as part of that process. So I can say, what is this system, right? So I have a system with one equation. It has one unknown and 6 parameters, right? Well, why do I have one equation, right? Then I have so many other equations in there, right? Well, I can ask it, what is this equation? So the equations that it has are the ones that are not simplified out, right? So I have this one equation, which is the capacitance equation, but I can also ask it, what are your observed? What are the observed states of the system? And you go, okay, we have all these other things in here as well. We have the ground.G.V is equal to 0, capacitance .N.V is equal to 0, right? There's all these other equations that it's found, and it's turned them into these explicit relationships. In fact, this is a cascading set of explicit relationships, right? You'll notice that the first thing, the equation that we're solving for, we're solving for capacitor.V. Once we know capacitor.V, you know how to get capacitor.V.P.V, right? Which is just by definition, capacitor.V is the same as the voltage of the positive pin, right? And you'll notice that then the resistance, the voltage of the negative pin of the resistor is defined to be equal to the positive pin of the capacitor, right? Because that is just this connection equation. And you can go down this whole set of equations and you can see how it's actually building up each and every variable, right? But under the hood, so that's really kind of just showing you a slight piece under the hood. But here we just have to say, okay, it is just a system with one equation in it, right? I build the ODE, and I solve the ODE, and I solve this ODE. When I solve this ODE, I can plot it, right? I don't know if I actually set up you did using plots before. I did this. Aha, I did, yeah. So I plot this, and then it's able to tell me, okay, here's the solution of the RC circuit. There you go, right? And you can see, okay, it's just this one. It's voltage is going into the capacitor, so I'm filling the capacitor, and it has this exponential decay in how fast it fills over time, right? But then you can go, okay, well, that is the solution of the capacitor, right? But what about the resistor dot voltage, right? We can ask the solution for. Did I spell it wrong? Oh, actually, I forgot to do the system name. So I can ask it, the system, give me the resistor dot voltage, right? And you can then see This is the voltage of the resistor. So you can then use the symbolic pieces as indexes to all these objects, and you can say, plot this in the solution with the index being the system.resistor.voltage, and there you go. It should be able to build this. It should be able to build what the voltage of resistor is automatically using the equations that are also known under the hood, right? Because it knows all the relationship between all the variables. It only solved for one variable, but it does know how all the other variables are related to what it solved for, right? So that's in the simplest version of that A-causal model. Oops, I lost my passport earlier today, so. Right, so you can see here that you just have to, you can then say, oh, I give it an initial condition, I have one of E, it has one condition, I build the problem and I solve it, right? So there you go. That's all you do for the RC circuit. You just literally just say, here's my resistor, here's my capacitor, here's my constant voltage, here's my ground, and from the standard library of components, you build them together, right? But now the next step to understanding is, okay, let's actually peel back from the surface here, and let's actually let's actually build all these components, right? So let me do this step by step then. I'm going to say, okay, so the first thing here, right, is that I have a pin. And a pin is an object. Remember, it's an object that has a voltage and a current associated with it, where the currents are the things that add like flows. They flow. They have this condition where you have two currents, they sum to zero, whereas if you have voltages, they're normal variables. So when you connect them, they just connect with equality, right? So that's what that set of equation means. Then you have, now you can start to build your first component. What is ground? Well, ground is just a pin which has one equation associated with it, which is just that G dot V is equal to 0, right? Well, I've already defined ground because I pulled it in from the library, but trust me that it ends up being the same exact thing, right? So now what is a one port, right? You can then see a one port is a thing that has two pins. It also has new variables, right? It has a V and it has an I, and then it has the three equations, right? That the voltage of a one port is the voltage drop across the one port. It's currents. The current coming in is equal to the negative of the current going out, and the current going into the one port is how we define as current, right? And so you get to go through this step by step, and these workshop notes are posted, so I can give you the link to them afterwards. We could do exactly what I showed in the slideshow, right? You just define, what is a resistor? A resistor is a one port that has a resistance and one set of equations, right? And if you then expand it out, and if you ask the question, what if you didn't use extend, right? This is this kind of hierarchical piece. If you didn't use extend, you could also just define the resistor as, hey, it's a thing with a positive pin and a negative pin, it has a voltage and a current, it has a parameter R, and it has four equations, right? It has how you define voltage, it's a voltage drop across the resistor. It has the 0 is equal to P dot I, so positive pin current is equal to the negative pin, or the current flowing out. Yeah, so all these three equations are true, and you have V equals I times R, right? So if you think about it, so this is something that has, right? If you think about it, this is something that has, let's see. So you have two variables here, and two variables here. So you have 6 variables involved, and you have 4 equations. So if you want to have a system that is well defined, you need to have the number of equations equal to the number of variables. So why does a resistor have less equations? Why does it have less equations than variables? Can anyone take a guess? Right, so if you want to have a well-defined set of equations to solve, you have to have the number of equations that you are equal to the number of variables, right? Because otherwise you have some variables that are not well defined, right? So here we see that this resistor has 4 equations for 6 variables, right? Because there's 4 variables inside of the pins and also 2 variables here. So why does a resistor, why does it work out? Why does it have 6 variables for 4 equations? Yeah, because of the connections, right? Because a resistor is not I cannot simulate a resistor, right? That doesn't make sense, right? I have to connect a resistor to something else, right? And when I do the connections, I get 2 more equations per connection, right? if you think about it, if you give one of those equations to the other component, one of those to the other component, right? You effectively, when you make two connections, you get two more equations in here, and that makes you have 6 equations for 6 variables. Okay? And so if you think about it, so that's why these acausal components are a little bit weird at first, right? Because you're just defining some things that are equal, and you're just like, how does that make a simulation? Well, an acausal component is not a simulation on its own. It's not a well-defined simulatable object, right? It has 4 equations for 6 variables. But when you connect a resistor to a voltage source and you connect it to ground, now you have enough equations to have a complete system, right? And so that's probably one of these pieces. Now you should be kind of getting to that 70%, 80%. Like, okay, now I'm starting to see why this is reusable, why I have these portions, and I see what the symbolic system is doing under the hood. Right? So since I've already kind of gone through this, I don't want to have to step by step here. But again, you build all these components on your own, and now you do this connections, and you notice that then what is the code of a standard library? This library of pre-built components. What is the code inside the library? Well, it's literally just things like capacitor is equal to this, right? There's no difference. This is the code that is in the standard library, right? And so when you have like these more detailed components, like okay, now we have a battery, right? Your battery might be described by the pseudo 2D dual Fourier-Neumann equations, right? Which is a large set of partial differential equations that then has a voltage on one side and the current on the side, right? You might have a very extremely detailed equation for how your component works, but at the end of the day, if it has a pin on a positive pin and a negative pin, you can stick it in here. It'll connect to other things, and then it says, okay, I solved these ODEs while solving this partial differential equation. It builds the whole detailed object, and it solves it. And so that's really all there is to acausal modeling, and that's why that's how you build these reusable components. So it's slightly different from how you might have done modeling before, right? If you've built models before, you normally think about what are the equations I'm solving for, and then you write down your equations to numerical solver, and you have to try to find out why the numerical solver doesn't love you, right? Well, here what you do is just say, this is everything that's true about my system. Just tell me everything that's true. And in fact, I can get some truths from someone else. Someone else has already told me these are the truths of a battery. Stick it right here. And what it will do is it will find what the actual differential equations are to solve. And then that will tell the solver to generate code to solve this, right? So it's a slightly different thing from writing code by hand. But again, the whole purpose of this is that if Vinny writes a code for a model by hand, and he has this set of ODEs, right? You can't necessarily take your ODEs and another person's ODEs and just copy paste them into each other because your indexing is wrong, for example, right? What you say is U of 1 is now U of n because you've moved it to the other part of the model. There's all these details. If you want to compose models, you have to handle how do you put these equations together, but also what things are equal between the models and how do you connect them, right? And what the acausal modeling system does is it handles all those little details about saying, hey, what you said in your model, what I said in my model, these variables are the same. These are the variables you added on. These are the new equations. These are the equations you can get rid of because they said the same thing, right? And so it's really doing all that process by hand automatically, right? And so to really understand then a bit for why, so once you start to understand that, your real question is, what the heck is structural simplification doing, and why is it so cool, right? Why is it so powerful? How is it able to do this, right? And that's really all where the true mathematics of the acausal modeling is, right? All the real power of Modeling Toolkit is then in this structural simplification. So I want to talk a little bit about a case here. So to kind of tell you about, to really talk through how, I want to tell you about this case on a pendulum in a Cartesian coordinates to really show you about that. It's not just doing simplification, but it's doing other transformations that are required because it turns out that this type of equation set, differential algebraic equations, are a hard thing to do. So what am I going to do? I'm going to show you that this model, right? So here's this model where I have a rigid rod. I have a rigid rod, and I have a ball on the end of it. And this is my pendulum. And so here's a pendulum in Cartesian coordinates. So I have a pendulum, and my coordinate system has an x. So I have a x value and I have a y value. Now you might think like, oh, when I did the pendulum, we always use polar coordinates like the angle theta. Well, I'm going to show you exactly why your physics teacher never gave you the pendulum in Cartesian coordinates. Once you see it in this origin, you'll understand why no one does it this way. But it's more fun this way, right? So how do you write the pendulum in Cartesian coordinates? Well, okay, so we have x prime is equal to v, right? So we have the velocity in the x direction is equal to x prime, and we have v prime is equal to, well, it turns out that there's actually, well, I'll show you this in a second. So the velocity in the x direction is here. So y prime is equal to v, y, vy is prime is equal to, we'll fill that in a second. It actually, because there's actually a fifth set of equations. So if I have a rigid rod, what also might be true must be true about the pendulum. We also have to have x squared plus y squared is equal to L, right? So you have an algebraic condition inside of here. So what ends up happening? Well, at different parts of the system, you end up having that there's a tension in this rod, right? This tension, the rod is either pulling to extend or contract, right? So it turns out that there's this tension variable T that is the tension in the rod, and then you also have minus G due to gravity, right? So this is actually everything that's pulling on the system, because you have a force due to gravity here, G, but you also have a force pulling back on the rod, which is the tension variable. So here are 5 equations that describe the Cartesian pendulum, right? Now, in polar coordinates, this is much easier because you don't have this constraint. If you're only talking about theta, right, then you just have a differential equation with respect to theta. But if you're doing this in Cartesian coordinates, you have a system where you have, 4 differential equations and 1 constraint equation, x squared plus y squared equals L, right? So let me find the set of notes I put together on this. So another way of writing this is just to say, here's the Cartesian pendulum where I have that the second derivative in x is tension times x. The second derivative in y is tension times y minus g. And you have the x squared plus y squared is equal to 1, right? So I'm just saying L is equal to 1. Okay? You might have never seen a pendulum written like this, but this is just equivalent to what, this is just a pendulum in Cartesian coordinates. It's just that there's this implicit force that is the tension of the rod pulling it back to the normalizing force for the distance, right? So let me pull this in here. So G is equal to 1. Oops. And I have these 3 equations. Well, let me take it out of, might be easier just to put these like side by side or something. Here you go. This should be easier. So, okay, so I have, let me pull in the import statement here as well. So I have the second derivative in x is equal to that, second derivative in y is equal to that, right? And now I say build the pendulum equations. Oops. And now it says the model pendulum has 5 equations. Well, yeah, because I wrote it out here in first order form, right? In the code, I showed it only in second order form, but as I described earlier, right? For an ODE solver, you can't actually solve these second order ODEs as easily. So you define things in terms of your first order ODEs in terms of the extension that I didn't mention, right? So what are the equations that it did? Let's actually ask it, what are the equations of the pendulum? And holy crap, those equations are nothing like what I wrote over here on the board. So what happened? Well, it's actually there's actually something really interesting going on under the hood here, right? So what's going on here is so first of all, let me just well, Well, let me just describe something at first, right? So if you look at the pendulum equations that we have written down, the last equation, x squared plus y squared equals L. Well, notice the thing that is weird here is what are the equations? What equation defines tension? Right? If you think about it, it's like, okay, this tells you how x changes. This tells you how Vx changes. This equation tells you how y changes. This equation tells you how Vy changes. And then you have x squared plus y squared equals L. So implicitly, x squared plus y squared equals L is telling you, given the current x and the current y, there should be a restoring force given by the tension. And so this algebraic condition right here is actually telling you how to define the tension variable, right? But it's implicit. It's because tension doesn't even show up in this equation right here, right? It turns out that if you try to stick that into an ODE solver in this form, it will fail. It will fail because you get a singularity when you calculate the Jacobian. Why is there a singularity when you calculate the Jacobian? Well, because t is not matched to this variable. I mean, that's like a very high level way of thinking about it, right? So there isn't an easy way to solve this with something like Newton's method. And so what can you do to solve this set of equations? Well, I can take the derivative of this expression, right? So then I have, x prime, 2x prime x plus 2y prime y is equal to L. And then I can take the derivative again, right? I can write out the derivative. What you'll see is I have second derivative terms, right? When I have second derivative terms, I can substitute in the second derivative terms, and now the tension variables are actually in there, right? So if let me do this all out in full, right? So I have like 2x double prime x plus 2x prime squared plus 2y double prime y plus 2y prime squared. And then I substitute here, what is x double prime? It's this equation right here, right? It's the second derivative with respect to x. So this right here is tension times x. And this right here is tension times y. Tension times y minus g, right? So if I differentiate my algebraic condition 2 times, then it is a function of tension. And now we can actually see that the algebraic condition actually meant that, 2 times the tension times x squared, yada, 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 is equal to 0. So it's actually a condition about tension, right? So, so if you try to solve the original formulation of the Cartesian pendulum, you actually get something that is a differential algebraic equation that's known as index 3, and is not solvable by any ODE solver. We do this, we differentiate this condition 2 times, we get an index 1 DAE. So each time you differentiate your algebraic conditions, you bring down what is known the index as the D of the DAE, and we can instead put this equation in there, and it's now solvable, right? So that's what I'm doing inside of these slides here. I'm saying, oh, if I actually wanted to write this Cartesian pendulum into a DAE solver, I can't actually write it as the original Cartesian pendulum. I write out the equations like x double dot is equal to lambda times x, x dot is equal to that. So the first 4 equations are fine. The 5th equation is this condition right here, which is x double dot times x plus x right? And why did I write it like this? Well, I wrote it like this because this is the second derivative of my original constraint, and that is required to be able to have tension show up in that formulation, right? Because now it's implicitly in the formula for x double dot right here, and it's implicitly within the y double dot equation, right? So I write it like this because if you actually call your ODE solver without doing that, it fails. And there's another slide I usually put in here. I guess I accidentally deleted that slide while setting this up. But so if you just write out this, x squared plus y squared equals 1 equation to go as out 5, you call the differential algebraic equation solver. It'll tell you, unstable solve, unable to solve, because it has a singularity. I change it to this set of equations, and now it's able to solve. But here I'm solving it with the pendulum from 0 times 0 to 500. Why did I do that? Well, we're letting the pendulum go back and forth, back and forth, back and forth, over and over and over. And then if you see what happens over a very long time, you see that the pendulum is actually moving. Can anyone guess why the pendulum ends up moving like that? Yeah, we know, well, we have an algebraic constraint. We have this algebraic constraint, which is not the same thing as x squared plus y squared equals L. Is that the second derivative of our algebraic constraint is equal to 0. So if there is a violation in our equations of x squared plus y squared equals L, at least we know the acceleration of that violation is equal to 0, right? Because it's the second derivative of the violation is equal to 0, right? So with this set of equations, it turns out that you can, this transformation, it turns out you can solve this differential algebraic equation. A solver will be fine with you doing this. It's just, it will have a natural drift in the system. So what do you actually do? How do you actually solve this set of equations, right? Well, if you actually look at what's going on here, this Cartesian pendulum, right? You write down x squared plus y squared equals L, but it takes you two different derivatives to finally, it takes you two different derivative expressions to finally get you to, hold on, this is equal to 0 here. It takes you two different derivatives before you finally get something that you can plug in tension, right? So what ends up happening if you understand these DAEs is that there's actually these implicit constraints, right? So in order to solve this DAE, you actually have to understand that you have these four ODEs. This is true. This is true, and this is true. Because if you have x squared plus y squared equals L is true, then you also have to have that its derivative is equal to 0, and you have to have that its second derivative is equal to 0. It turns out that these equations are actually new equations. The ones that you derive have actually new information in them. So if you want to solve this in such a way, so that way you end up satisfying this equation right here, well, you need to make sure, in order to represent this to a solver, you need to have 5 equations for 5 variables. What this means is that this set of the Cartesian pendulum is actually described as a set of 7 equations for your 5 variables. If you choose the wrong 5, some of these choices are not solvable. Others of them have numerical drift. Can anyone try to guess what a set of equations for, a subset of these 7 that you might be able to solve in a numerical solver that doesn't have numerical drift? Well, let's keep these 3 equations, right? Because each of those are, x squared plus y squared equals L, and, so all these equations are constraint equations, right? So it sounds like it's good to make sure all of our constraints are true. But if you have this constraint and you have this constraint, well, if you know how x is defined and if you know how x prime is defined, then if you know how x is defined, well, technically, if you know where you are in x, that is actually telling you where you are in y. Because x squared plus y squared equals L, right? So you don't need to solve for x and y. You might as well only solve for x. So you might as well delete your y prime equation because x prime tells you what y prime is through this constraint right here, right? And in fact, the derivative of your constraint means that if you know the derivative of x, then you actually know the derivative for y. So you actually don't need this equation right here. So if you then look at what Modeling Toolkit did under the hood, you want to go, okay, how smart really is this thing, right? If you look at what it did, you give it the equation for the pendulum, and it will find out automatically that the right variables to solve for is what actually chose. We're going to solve for the derivative of y. We're going to solve for y, and we're going to have our other 3 equations be exactly these 3 constraints right here, right? Because everything in x is defined through these constraints. And if you solve your equation using this formulation, what you actually see is that you have a pendulum that has no drift at all. It stays exactly on this line. So again, this is probably why you did not do the Cartesian pendulum in your, first, your 3rd grade physics class, right? You used polar coordinates, and this is why you use polar coordinates, right? Because this is probably a bit too much for a high schooler, but here you go. This is actually how you do the Cartesian pendulum, right? So here you can see that if you actually use Modeling Toolkit now within something like Pluto notebooks and such, it'll actually print out the LaTeX, and you see, you give it this set of equations for the Cartesian pendulum, and it will actually tell you, hey, the actual equations for this is these 3 algebraic equations and these 2 ODEs, right? And so, yeah, so that's what's going on under the hood. So there's all sorts of things going on inside of the structural simplification, which are improving the numerical performance. It's really hard to describe what the algorithms are in general, but hopefully that gives you a feel for that there is something that is really going on under the hood, so that when you give a whole set of equalities along with the differential equations, it's doing something that is quite detailed in order to make sure that what you get is actually numerically stable. And how am I doing on time? All right. Oh, really? Okay. So I did cut a huge portion from the Julia conversion and went straight to the modeling. Yeah. So then for this one, then I get to talk about consistent DAE initialization, right? So what is consistent DAE initialization of DAEs? Well, let's think about this pendulum that we just wrote down, right? So in this pendulum, how do you define the initial condition for the pendulum? Well, okay, so you might have said at first that, hey, the way that we're defining the pendulum is we have x, we have y, we have x, we have the velocity in x, and we have the velocity in y, and we have a tension variable, right? But when you actually go through and write and find out how the equation is defined, you actually find that you have two ODEs and you have three algebraic conditions, right? So now let me ask again, what is an initial, how would you write down an initial condition of the pendulum? Well, you could give a value for x and y and vx, vy, and tension. But if you do give all 5 of those variables, you have to make sure x squared plus y squared equals 1. You have to make sure that, the x sub t, x, y sub t, y is equal to 0. Right? You have to make sure that a lot of these conditions are actually satisfied because, again, this is a set of equations that has 2 equations for how things are evolving and 3 equations that must be satisfied at every time point. And so what you actually have to do in this system is you actually only need to give two conditions, right? You just have to say what is the initial y of the pendulum and what is the initial velocity of the pendulum. If you give me the initial y, I calculate x using this equation. I calculate the initial velocity in x using this equation, and I calculate the initial tension using this equation, right? So all the variables are given. So in the way that I've written down these equations, you only need to give me the initial y and the initial velocity in y, right? Now, then your next question should be, well, that isn't how I thought about the pendulum. What if I gave you the initial x and the initial y? Well, and if you think about this in terms of an acausal system, right? Now you think about this acausally, right? The acausal system took all of these different components that you gave it, and it solved for some subset of the equations that it believes is the best thing to solve for because of some crazy numerical algorithm for stability. And now the question that you should ask is, okay, what initial condition do I give this? What if I knew that the initial velocity of the resistor was equal to 0? It's like, oh, well, this ODE right here is actually what it found was actually it's solving an ODE for the initial velocity of the capacitor. So you define the wrong initial condition. Like you have to go find the other one, go calculate it out, right? No. So the system would be almost impossible to use if you had to actually find what the right variable to define was, right? Because it's almost random to you at this point, right? You just kind of say, hey, here's my set of equations, and it will do something to these. And what variables it needs to use is effectively random to the user, right? Because it's all some result of simplification. So the real question then is, how do you represent how someone has to give you initial conditions such that you can satisfactorily find out your initial conditions that you actually want to use, given what the user is describing to you, right? And this is the consistent DAE initialization. So let's say we have these 3 equations. Well, what would happen if let's say we have these 5 equations that we're solving with, right? Now, what would happen if you give it what would happen if you give it an initial x and an initial x sub t? Well, it can't actually use those, right? Because again, this is an ODE that only has 2 ODE states in it, right? It's solving for y and y sub t. So so it's not x is not an equation of your system anymore. But if I was to give it x as an initial condition, what do you think it would do with it? What would you do with it in order to use these ODE equations? Yeah, so if you gave it an initial x, then you go, oh, hey, I know that 1 minus x squared minus y squared is equal to 0. So I can calculate what the initial condition in y is, right? So this is then this a consistent initialization system. So you can say, okay, I can give it an initial x, and I can give it an initial y, And from that, it will give you an ODE, right? It will give you an ODE. And if you solve this, it will then be able to solve it. And it says, okay, all these conditions are always satisfied, right? Because what it can do is it's able to say, okay, no problem. You gave me X and Y. I solve for I solve for the initial conditions I wanted, and then I go forward, right? But what this means then is that there is actually a system in there, right? There's a Newton system, right? A Newton nonlinear system that is formed, which is for the consistent initialization process. And I want to kind of show you a little bit of that. Let me see. So initialization and modeling toolkit DAEs. I believe this just uses the pendulum as well. All right, so when I want to build the numerical, so remember the syntax is this builds the symbolic ODE system, right? Now this builds the numerical ODE system. And what I do here is I say, okay, my numerical ODE system is defined by having an initial condition of y is equal to 0 and d of y is equal to 0. And it's able to take that and then be able to run an initialization process or build an initialization process that's then able to handle such a solve. So let me then show you the solve here. Right. So here I'm showing you that, okay, I'm giving it x equals 1, I'm giving it y equals 0, and it takes this and it's able to solve it and it says success, right? And now what it's actually doing, I can take this ODE problem here. Let me just call this prob. And if you check the documentation, you can check prob.f.initialize hold on, keeps on prob.f.initialize sys or initialization prob. Hold on, get property. Oh, property names, sorry. You'll see that inside of here, there's initialize prob. Oops. So there's a nonlinear problem in here for the initialization, and it has a .f.sys. So there's this system in here, which is the initialization system. And what did it do? Well, the initialization system is saying, oh, I have to satisfy these three constraints, and I have that as my observed variables. Oops. Prob.f.initialize prob.f.sys. I have as my observed variables, I have that y is equal to 0, x is equal to 1, and I also have this condition because this is one of the other implicit conditions from within the ODE, right? Right, so that the second derivative, right? So this is just one of the ODE conditions itself, right? So you can see that, okay, it's able to construct and say, okay, I know what has to be true at the beginning here, and so I'm going to be solving for these three variables, right? And so if you can actually ask it then, for example, you can actually ask it, what are your unknowns, right? The unknowns of the initialization are y sub t, x sub t, and lambda, which is actually different from the unknowns of pend, right? So the original system is solving for these 5 things, but during the initialization, you're solving for a subset of them because if you're given 2 of them, then you can figure out what the other 3 are from the algebraic conditions, right? And so what you can see is that the initialization system, this process of initialization is not defined exactly just by the ODE, but it's also defined by what initial conditions you've given me, right? Because if I give it other initial conditions, right? So if I say, d of y is equal to 0, so if I give it other initial conditions, Right. So what is this saying? What is it saying? It's saying that the y at 0, 0 is either missing from the variable map or missing from the system's unknowns or parameters list during the initialization. What this is telling me is that it doesn't actually know of a guess for it, right? So I then also had to tell it this d of y is going as, or no, it was saying that y was missing, right? So saying this, I need to add this here. Now, can anyone guess why I need to put this thing called a guess here? Right. So let me show you now the unknowns. So the unknowns of the prob.f.initialize problem, right? The unknowns of this initialization system now includes, right? It used to be up here. So in the original form, the unknowns were y sub t, it didn't know. But now if I give it the initial velocity, I need to have, it will now solve for y from y of t, right? So what is this guesses here doing? Can anyone guess what guesses means? Yeah, you have to initialize the nonlinear solve, right? Because if you do something like a Newton's method, right, you have to have a starting guess for what your solution to the algebraic conditions are. So now that we are solving for what y is, right, from the other algebraic conditions, we tell it what d of y is, but we do need to give it a guess for the algebraic solve, right, the Newton solve for the initialization, right? And so that's why the system, it's kind of a bit weird at first to just be like, okay, what do I need to find initial conditions for? Oh, it's asking for guesses. What are these guesses? Well, in a lot of cases, you could probably guess if the guess is equal to 0 and the initialization process, Newton's method will find out what to do, but you always have to start Newton's method at some value. And so if I left this off here, right, that's what it's saying. It's saying that, this y of 0 guess is missing from the variable map, right? So I need to put it into this map of the variables, right? And so you can see that every variable either needs a set value or a guess, right? It's either something that's being solved for in terms of the initialization problem, or it is something where you give an initial condition to the initialization problem, and it's either something that is being set as a set equation via the in the initialization, right? It's either set as a constant or some equation, or it is something that you give as an initial value to the nonlinear system that is solving for the initial values, right? But this means that so there's a lot of different cases I can show. Right. So what if I give it just one equation? What if I just say that x is equal to 1, right? I say my only initial condition is x is equal to 1. Well, in that case, you have an underdetermined system, right? Because if you have only x is equal to 1, then you have to find all the other variables from just that one equation. It turns out that you have in your initialization system, you have three equations for 4 unknowns. So let's try to understand this. What are the 3 equations for the pendulum inside of this initialization equation or system? What are the 3 equations that are in there? Well, remember back to the pendulum, right? We ended up with a system which has two ordinary differential equations and 3 algebraic conditions, right? So if we have this system right here, well, these are 3 equations in the initialization, right? All 3 of these need to be satisfied at the initial time point, right? And so those are our 3 equations, and we have 4 unknowns. The 4 unknowns are, v of x, y, vy, and lambda, right? So you always need, in order to be able to have a solvable system, you have to have the number of equations equals the number of unknowns. And so this is why you needed 2 initial conditions if you only have 2 ODEs here, right? Because you have 2 ODEs and 3 equations for 3 unknowns, right? So if you only give it one initial condition, it will then throw you this warning that says the initialization is underdetermined. And what it means is that you need more initial conditions. Like, it's not a fully complete system. It can give you initial point, right? It can find you initial point that satisfies all these equations. It's just that there's infinitely many solutions to that, right? So it will find an initial point that does that, and you can solve it. But it turns out that is underdetermined, right? You have the other situation, which is overdetermined, right? So again, this is, if you think about this Cartesian pendulum, right, you might say that x is equal to 0, or y of 0 is equal to 1, right? And you might have that, y prime at 0 is equal to 0, right? You just write down a bunch of conditions, and now, it's totally fine to write them down as long as it's actually a consistent set, right? And so here, what you see is that, in the initialization problem, you had 4 equations for 3 unknowns. One of these extra equations is the one that's determined by the derivative system, right? And there's only 3 unknowns because you've previously defined 3 of the variables. So the derivatives are actually handled in a pretty unique way. So that's why that one is still an unknown. But so what this is basically telling you then is that you've defined 1 extra initial condition. But if you then call the ODE solver, it's totally fine in this case, because if you go through the algebraic conditions, this set of conditions is actually consistent. So it's perfectly fine, right? So if you go to the if you do something like the A causal model of the RC circuit, you can write down, the initial voltage is equal to this, the initial capacitor is equal to this. You write down tons of equations in there. It will give you this warning, right? This warning is actually probably the most, in most codes that I see that come out of Modeling Toolkit where someone has done something which is kind of iffy, they will always have this warning, right? Because you've defined a whole bunch of these extra conditions. You didn't need most of them, but if all of your equations are actually true, it will still work out, right? The problem is that if it's not true, right? Because if you have this this over-constrained differential algebraic equation, right? If you have more initial conditions than you have algebraic equations, then you end up having, there is not necessarily any solution to that set of equations. So here I wrote down, x1 is equal to 1, or x is equal to 1, y is equal to 0. Derivative of y is equal to 2, lambda is equal to 1. It turns out that is not a consistent set right? There is no way for me to find a derivative of x for the initial point such that all of my algebraic conditions are satisfied, right? And if you plug all your equations in right here, you basically have that 0 is equal to 1 shows up, or 0 equals to 1 shows up in one of these equations, right? There's just impossible to ever satisfy that set of initial conditions that are given to you, right? And so what will happen if you do this in such a system, what will happen is it will let you build the system, right? Mathematically, the system that you built, it's okay as an ODE problem, but when you call solve, it will try to do this initialization process, and this will then give you this return code, initialization failure, and boom, and then it will stop before ever doing the first step. Right, and so probably the biggest thing that I see people who are first trying to do A causal modeling, the first problem that they seem to run into is, hey, I got an initialization failure, and I had this warning that I had initialization failure. I don't understand what's going on, right? This is what's going on, right? That when you are dealing with an A causal model, there is some set of equations that it's solving for. You need to really think about what kind of equations, what is constrained, how many things are constrained, right? Because it's really the number of things that are not constrained need to be the number of initial conditions that you give it. And if you gave it too many initial conditions, then there might be no way for your initial conditions to be satisfied, right? Because if you think about, for example, the RC circuit, right? If you think about the RC circuit, if you tell me the velocity right here, or the voltage right here is equal to 1, you tell me that the voltage right here is equal to 2, right? Like, no matter how I try to find initialization for this, those two voltages are supposed to be equal. So this is not satisfiable, right? And this is how it throws that error. So this is, when you start to do these A causal modeling systems, I think the thing that most people get tripped up on is understanding what is going on with the initialization. I got an initialization failure. Why did I get that? And it almost certainly is because you wrote down some equation that is not solvable, right? And so again, so it's not even that you just have to have the number of equations equals the number of unknowns. You also have to be careful about which ones you get, right? You can't just give any possible initial condition, because giving the voltage of the positive pin of the resistor is almost the same thing as giving the voltage of the positive pin of the voltage source, right? So you need to make sure that you give the initial conditions for these things that are not necessarily computable from one or the other. And so that is something that can be a bit difficult about an A causal system that you do have to work through. And you had your hand up for a second?
Yes.
Mhm.
The right like initial condition, but the guess for the other variables is not so matching. So
Yeah.
eventually you can also in the same way.
Mhm.
So you have like the degrees of freedom, it's okay, but it's not so constant. So with the initialization, so we will give you the same problem, the same initialization variable, but not because you don't put a really a guess, but it's because you didn't put a really good guess.
Yeah, yeah. That is something that is possible, right? So it is completely possible that when you try to solve the initialization problem, it will, so the case I'm showing here is like literally unsolvable, right? You could also have the case where it's just numerically very difficult, right? Because it's running a Newton's method to find initialization and trying to do it to the ODE solver tolerance. And if the Newton method for that given guess is not able to converge to the tolerance to a solution, then it will say that had initialization failure, right? It's not distinguishable in the numerics whether it's a failure of the numerical solver or of the user's input, which is the thing that makes it a bit difficult, right? I wish we had a better way to kind of distinguish between the two, but I can tell you that from like 99.9% of issues that I've solved online, it was a user's issue first. So it can, I do know of exactly one system. It's an active suspension model on a car. So like it's a car suspension system, which ends up so that way that at the initial point, there's a singularity exactly at the solution. So yeah, like that one is a numerically very stiff, difficult initialization problem to solve. And then we're working on new tooling to handle that, yada, yada, yada. But yeah, if you actually run into this, the first thing that you should think is, I probably made a mistake. But yes, numerically, you can end up in a case where it's like, and because the other case that happens is it could be numerically solvable, but just very hard for it to solve to the tolerance of your ODE solver, right? Yeah, because so what it'll do, right, is it'll build this it'll build the system that's like six equations for 5 unknowns, and then we'll do a least squares problem fit, right, using something like Gauss-Newton's method or something of the sort. And most of the time, it should be able to tell you whether it's solvable or not, but there are some difficult edge cases in the numerics. So yeah, I think that that was the last piece I kind of want to go into. Just this handling of the initialization problem that shows up in these acausal models. So I think that's kind of like a general introduction to acausal models. And now, if you go all the way back to, the very beginning here, you see that, yeah, we have a whole bunch of extra compilers for these really big models. And, what we have teams that have been building out, these HVAC systems and battery systems and all sorts of systems where they can have literally these 200,000 equations that can fit into any circuit or car system and all that. But this is how it's working under the hood. It's writing equations upon equations upon equations, and we have compilers generating, better and better things for solvers, and it's a continuing process. And we're working with a lot of groups, especially with Vinny right here, to be able to extend this to new modeling domains. Because, we can start to think about this. It turns out that this way of doing modeling encompasses many other modeling domains, such as process modeling and simulation. Right, you can incorporate, all the different reactors and such of process modeling in these kind of flow sheets. Think like the Aspen type of models. Right, it can be incorporated into one of these acausal modeling systems. And the structural simplification actually gives you the exact same process that GEPROMS is doing under the hood, right? There's an equivalence between them. So we're kind of building it out to all sorts of different modeling domains, and hopefully that is a useful tool for you sometime in the future. So thank you.
Thank you, Chris. Very deep dive introduction into the acausal process modeling. Very good examples. The pendulum, seems like very simple, but when you try to solve it, you see it's not simple.
Yeah, the pendulum is a great example where you just say, oh, I think I understand how math works, right? And then you just go, calculus is hard.
So following your presentation, I'll be showing a bit what we're showing in JuliaClone about how to do this into the context of chemical engineering. Showing a bit on how to do CSTR with streamed object and how that can be put together to process simulation. So it's going to be not so long and deep as Chris did, but still I hope it's useful. It's still recording. Perfect. I think my screen is visible now, right? Yep. Okay, so these very short presentation demos about how to put together these concepts Chris talked about acausal process, acausal modeling, using modeling toolkit for things that chemical engineers usually do, which is simulating chemical reactors, flash separator units, and that kind of things. So we typically have in chemical engineering more variables in the electrical circuit that Chris showed. So he mentioned current and voltage, but then when you're dealing about the process in chemical engineering, you have a pressure, temperature, we have mass flow rate and compositions as well going on. But the idea behind it is pretty similar to what he mentioned about electrical circuits. So that was a talk we gave at JuliaCon. So the idea, the name of it is a process simulator.jl. It's a differentiable chemical process simulator. So the idea is to build a library for chemical engineering process simulation that has a whole library of unit operations that you can connect and simulate your process. In the same way you have the modeling toolkit standard library, you have the library for electrical components, you have the library for thermal components, and have the library for some mechanical components as well. So in this demo, we just wanted to show how you can simulate the startup of a CSTR, continuous starter tank reactor. So for the synthesis of propylene glycol, it's just a chemical which has value for the chemical industry. So basically, one of the assumptions you have no isothermal. Typically, you have a cooling jacket to cool down the reaction to prevent a runaway of the temperature of the reactor. Because if you're not unable to get all the heat that generates in the reaction, the temperature blows up and you end up in a dangerous scenario. So basically, we are dealing with flow-driven simulation. There's a whole subject on how to simulate a chemical process flow sheet. You can either assume that you have perfect flow control of the streams, or you can put valve systems and then calculate flow from pressure drop. So they're pressure-driven usually way harder to simulate than flow-driven simulations. But for this purpose here, we're just going to show how you can do this with assuming that you can have perfect control of the flow. So that's a chemical reaction network, a very simple reaction. We react propylene oxide with water, and we get our product. So typically, hold on. Yeah. So that's my graphical representation of the system. We typically in chemical engineering, we have first order ODEs, and we have some algebraic constraints which are related to physical properties of the system. So differential equations are usually related to energy and mass balance. And algebraic equations are usually related to physical chemical properties. So, for instance, enthalpy is a function of temperature, pressure, and also composition in the mixture. Oh, hold on, I'm not sharing my screen. Oh, that's bad.
Only physically. The call in Teams.
Okay, I can see it. Oh, okay, I see.
You can go on. I'll fix it.
Yeah. Okay. So you can see my screen from the video, but not from. So we have typically differential equations, mass and energy balance, and we have algebraic equations which are related to physical properties. So typically you get those properties from equation of state. And to get those properties from an equation of state, you need some implementation of those equations. So in this process simulator, we use in Claypron.jl, which is a library in Julia that has a lot of different equation of state that you can use to calculate those properties for several substances. And we also assume that we have a typical driving force for heat from the jacket to the reactor using these algebraic expression here. Basically, we go on with methanol, water, and propylene oxide. You get propylene glycol and some remaining reactants, but we have to cool it down because the reaction is exothermic. So as you can see from the picture, we have a material stream, which is the stream going into the reactor. We have an outlet stream, the stream going out of the reactor. By this picture and making an analogy with what Chris said, we can see easily that in a reactor we have two material ports, things that allow you to either inject or collect matter from the reactor. And as you have heat exchange, you also need some kind of thermal port to account for heat transfer. Well, so the material source, typically, if you have ever used Aspen or any flow sheet simulator, you can initialize a material stream, and you have to specify some things. One of them is the substance you're dealing with. The other is the equation of state you are dealing with. You want to use to model the properties of the system. You have to specify pressure, temperature, composition, and possibly flow rate as well. So from this specification, you can get out all other properties using an equation of state. So enthalpy, entropy, gas phase fraction, molecular weights, density. So in this case, we're using Clapeyron that enables us to get all those properties by specifying these other conditions. So these are not the only subset of conditions you can specify. You can specify, for instance, pressure and enthalpy. There's a minimum number of conditions you have to specify, but for here, we're gonna, the most typical one is pressure and temperature. So for those systems, well, we have to load some libraries, Clapeyron and our library process simulator. So then you also have to specify the substance you're handling with. So water, methanol, propylene glycol, and methyloxyurane, which is propylene oxide. So then you can instantiate the Clapeyron model using the substances and also an ideal model. That's very specific for Clapeyron, so that's beyond the point of the presentation. So with this, we can build our material source objects. As I told you, we need the substances. We also need a thermodynamic model for which we're going to use to calculate the properties. So I specify pressure, flow rate, composition, and also the temperature. Here, all of the equations, I think Chris mentioned this feature that now you can print out the equations on the notebook itself. We have a bunch of equations describing those properties I mentioned. Then we also have to specify how things react in the system. So I have a collection of substances. That's a typical power law reaction kinetics. So here I can specify the activation energy, and also can specify the pre-exponential factor in this power law. Then I can also specify the stoichiometric coefficients. So water is consumed, so I put here -1. Methyloxyurane is also consumed, I put -1 here. And propylene glycol is produced, so I put +1 here. So here's the exponent of the power law that governs the reaction rate. So the only thing that affects the reaction rate is the concentration of methyloxyurane, which is the limiting reactant, because I'm making a reaction with excess water and a bit of methyloxyurane. So then that's the reason why I put the exponent 1 here. And then I can name the reaction object, the name I want, propylene glycol synthesis. Then I can build the CSTR model. So the CSTR is a tank with a styre. But once again, I have to specify the substances. I also have to specify in which phase I want the reaction to take place. So I also have to specify the cross-section area because that affects the height of the liquid column that affects the flow. And I have to pass some gases here. I'm using gases for the concentration volume and also the flow rates coming out of the reactor. So in the same way, Chris showed that they can connect the components in an electrical circuit. You can also connect the material source out connector with the inlet connector of the reactor. And that basically says that whenever you connect the two, the pressures are equalized and also so the sum of the flow rates are 0. So that's how things happen when you connect two components with flow streams. So then I end up with 194 equations.
which I'm not going to solve for because before it, you have to run the structural simplification to get the minimum number of equations you have to solve for it. Then you can get out of all the relationships by algebraic or any other constraints you have in the process in the system. So when you run structural simplification on this system, you get basically some 5 differential variables, mostly related to the mass balance. And you also get some algebraic constraints, which are related to either property calc. For instance, this one here is how you calculate relate the number of moles and the volume and the density. So here's how you relate the number of moles, the concentration, and the volume. That's very straightforward. Then you have to specify initial conditions. So you have to specify the holdup in the reactor. So I have a holdup of, I have a lot of water in my reactor, and I have a little of one of the reactants, which is methyloxyurane, which is the limiting reactant. And I have to specify also the temperature in the content of the tank. So once I specify the system of equations and the initial conditions, I have to say how long I want to integrate in time. Then I can build a problem to be solved. And then once I solve the problem, I have to specify a solver and a tolerance for that solver. He is using these, I think it's a implicit multi-step solver, KNDF, right? Right, Chris? It should be it.
It's an implicit PDF.
Yeah. So I set up a very quite standard tolerance, 1 to the -8. And then I can get the solution for it. So that's the temperature over time for the startup of the simulation. So we used a very, we used a rigorous physical property library. We use PCSoft as one of the equation of state to model the mixture, the liquid mixture. And this is all put together with the mass and energy balance. So typically, if you have gone in a reaction engineering course, you usually say that the liquid behave ideally, and I have entropies only depending on temperature and not depending on the composition. So you can make these, you can get rid of those assumptions and model real systems, because most of the real systems, including those ones where you have methanol and propylene glycol, the mixture is not ideal. So you can get reliable simulations, and also making sure you're solving only the minimum number of equations you can have for the system. And you can do a bunch of analysis after this. You can plot the reactor temperature, you can plot the concentrations over time. And this is a dynamic. Of course, if you want to make this a steady state, you can do pretty much what Chris was talking about. You can also specify derivatives at the initial condition and making sure you're solving for the steady state. Or you can just frame it as a steady state problem and make all derivatives equal to 0 from the beginning and then solve it for the algebraic equations. You can also plot the phase space of the concentration and temperature to see if you have bifurcations. And I think there's a library in Modeling Toolkit for bifurcations and analysis as well. Yeah, so it was pretty quick just to show how you can use it in a very quick demo, how to use it in the chemical engineering process simulation. So the idea is you build the components, you connect them together with the connect syntax, and then you simplify the system, you solve for the equations, and the remaining variables you didn't solve for, you can just call using symbolic indexation from Modeling Toolkit. Thank you. So I'm also presenting the host of the meeting. So just finished presenting, and then I would like to thank Chris for the great talk. Very deep tutorial and a demonstration on how a causal component-based modeling can be used to model systems, and how you can reuse the things you have already coded to prevent you to having to rewrite code every time you add a new component to your system. So that's a very powerful modeling tool. And as Crystal is not as popular as causal component-based model, but hopefully in the future that is going to be a shift in that scenario.
Should be.
Yeah.
I think it's a lack of tooling issue, right?
Yeah.
I think if the right open source software exists, people will use it.
Yeah, I truly believe in this as well, because it's a very more intuitive to write down equations like this than having to put these blocks, integrators and multipliers and summation blocks. Because it's more familiar than for engineers to do things like this. than having to build those blocks of almost incomprehensible things like integrators and summation blocks. Yeah. So I think I might stop sharing. There you go. How do I stop the record? Stop recording. So I see some people